Welcome back to the Tech Talk podcast, where we dive into the intricate world of technology and software development. Today, we're tackling a vital topic in database management, transactions, and isolation levels. If you've ever wondered how databases maintain data integrity while allowing multiple users to interact simultaneously, this episode is for you. We'll break down what transactions are, the challenges of concurrency, and the various isolation levels that databases use to manage these transactions effectively. Let's kick things off with the basics. A transaction in a database is essentially a sequence of operations that are treated as a single logical unit of work. This could involve anything from inserting a new record to updating existing data. The key concept here is atomicity. Transactions must either complete entirely or not at all. This guarantees that the database remains in a consistent state, even in the face of errors or unexpected failures. Now, as we discuss transactions, it's important to consider how they interact with one another, especially when multiple transactions are occurring at the same time. This is where isolation levels come into play. Isolation levels help define how the integrity of a transaction is visible to other transactions. The challenge is to allow concurrent access while avoiding problems like dirty reads, non-repeatable reads, and phantom reads. Let's walk through the steps involved in a typical transaction. First, a select query is executed to check if certain conditions are met. For example, it might verify whether there are enough resources available, like doctors on call or rooms for booking. If everything checks out, the application decides to proceed with the operation, which could involve inserting, updating, or deleting records in the database. However, issues can arise when transactions run concurrently. Imagine two transactions trying to book the same room at the same time. If both transactions check the availability simultaneously, they might both proceed, resulting in a double booking. This scenario is known as a write skew. To address these challenges, databases implement various isolation levels. The most basic level is read committed, where a transaction can only read data that has been committed. This prevents dirty reads but doesn't protect against non-repeatable reads or phantom reads. Next, we have repeatable read, which guarantees that if a transaction reads a record, it will see the same value if it reads it again during its execution. However, this level can still be susceptible to phantom reads, where new records added by other transactions can affect the results. The strongest isolation level is serializable. This level ensures complete isolation from other transactions, executing them in a way that the final outcome is the same as if they were executed one after the other serially. While this eliminates all race conditions, it can lead to performance bottlenecks due to increased locking and waiting. So why don't all databases use serializable isolation? The answer is performance. Implementing serializability can be resource-intensive and can slow down the system, particularly in high concurrency environments. To combat this, databases often employ techniques like two-phase locking, where locks are acquired before a transaction begins and released afterward, or optimistic concurrency control, which assumes that conflicts are rare and only checks for them at the commit stage. Now let's discuss how transactions are executed. Traditionally, databases have operated in a multi-threaded environment, allowing multiple transactions to run concurrently. However, a newer approach is to execute transactions in a single-threaded, serial manner. This method can simplify the concurrency model and potentially enhance performance by avoiding the overhead associated with locking. This shift has been made possible by advancements in technology. For instance, with more affordable RAM, it's now feasible to keep entire datasets in memory, which allows for quicker transaction processing. Modern databases can also handle short OLTP transactions efficiently, since they generally involve fewer reads and writes. But there's a catch. When transactions require user input, they can slow down and become inefficient. Most databases avoid long-running interactive transactions, opting instead to keep them short and commit them within a single request. This means that a new HTTP request initiates a new transaction, which helps maintain performance. Another important consideration is how transactions are structured. In traditional setups, transactions are executed interactively, with queries sent back and forth between the application and the database. This can lead to significant delays due to network communication. To mitigate this, some systems use stored procedures, where the entire transaction code is submitted to the database ahead of time. This approach minimizes delays and can boost performance, provided all necessary data is in memory. Stored procedures have been part of the SQL standard since 1999, but they've faced criticism for being difficult to manage and lacking modern features found in general-purpose programming languages. However, recent developments have seen databases adopting more contemporary programming languages for stored procedures, enhancing usability and performance. In summary, understanding database transactions and isolation levels is essential for anyone working with data. Transactions ensure data integrity, while isolation levels help manage concurrency and prevent issues like dirty reads and write skew. Although serializable isolation provides the strongest guarantees, it can impact performance, which is why various techniques like two-phase locking and optimistic concurrency control are employed. As technology continues to evolve, so do the strategies for managing transactions, with single-threaded execution and stored procedures gaining traction. By keeping up with these developments, developers and database administrators can ensure their systems remain efficient and reliable. Thanks for joining us for today's episode. We hope this discussion shed light on the complexities of database transactions and isolation levels. If you enjoyed this episode, don't forget to subscribe and share it with your fellow tech enthusiasts. Until next time, keep exploring the fascinating world of technology.